Self-consolidating concrete is concrete that is able to flow and consolidate under its own weight.
High-strength concrete is one that has a compressive strength greater than 50 megapascals.
Currently to this day, there are more than 1,500 differing mixtures that can be used to produce various types of self-consolidating concrete, all with varying mechanical properties.
The applicable materials of high-strength self-consolidating concrete vary depending on the job at which the project is applied. However, as a general rule of thumb, aggregates should be well graded and kept to a minimal size due to the aggregates being weaker than the cement matrix. Water-cement ratios should be lower to increase strength. Superplasticizers should be utilised, however, to combat the lower water-cement ratio, as the workability needs to be increased for the self-compacting requirements of the mixture. Furthermore, the addition of pozzolans as a cementitious substitute increase the strength performance. However, keep amorphous silica to a minimum due to the increased sticky nature of the mix.
Compressive strength is one of the main factors that creates a basis for design rules. In many cases, the compressive strength that can be classified based upon cube strength or cylinder strength, both of which are displayed in the figure. When vibrated concrete VC is compared to an SCC sample at the same water to cement ratio, SCC is seen to have a higher compressive strength of up to 15% for the cube and up to 5% for the cylinder. This improvement in compressive strength is due to the enhanced interface between the hardened paste and the aggregate in SCC. The figure displays the information graphically. In order to evaluate the tensile strength of SCC, three main and well-known methods of testing is used. All the experiments are conducted to measure and record the resistance of the SCC breaking under tension. In a sample of test subjects, data obtained displayed that during the splitter tensile test, SCC that had the limestone filler had, on average, 15% greater tensile strength than regular vibrated concrete.
There have been many applications of high-strength SCC in recent years. This has included high-rise buildings, roads, bridges and rail projects. One example is the reconstruction of the Roseville Railway underbridge. Being in a cramped environment, this required SCC for the casting of two transfer beams 36 metres in length. The table seen here was used for ensuring the concrete could fulfill its requirements. As you can see, the table looks for certain properties of the material that are essential. The slump test and J-ring tests were two tests applied. These tests align with what is required through AS 10123.3.5 methods of testing concrete, specifically with SCC. Overall, this application of SCC was one of great success.
These examples show great ways that self-consolidating high-strength concrete can be used. I investigated ways that this type of concrete can be improved, as well as its faults and the faults of concrete in general. The main fault is that most batches are quite specific in their mixture, and that some batching plants don't want to make it because there is too much riding on it being right. This is made up for due to its high strength and that it doesn't have to be vibrated during placement. I also investigated the problems that are common with regular concrete, such as reinforcement corrosion. High-strength concrete is good in this area as it is less porous, and carbonation affects it inside where reinforcement is slower. Australian Standards 3600 covers this, as shown here. I also investigated the impact of carbonation in concrete in general, as it makes a good carbon sink, and looked at the process of carbon capture and storage, and how it can take away the carbon that is normally released in the production of cement. This could make concrete manufacture a carbon-negative process. In short, I think self-consolidating high-strength concrete is a very good option for concrete. Other options should also be considered. Also, there's still a long way for it to go, and a lot more research needs to be done.